Hello, this will be my presentation on artificial blood vessel design for use in a product. So the first thing we need to consider when creating an artificial blood vessel is biocompatibility. Biocompatibility is a material's ability to not react within the human body, so not cause allergic reactions, not cause anything that would be a harm to the person. A few good materials for this that I chose to analyze for this project are silicone, polyurethane, and PET. So the reason I chose those are because they have already been used in artificial blood vessels in the past, and because they, for the most part, had very good biocompatibility. Starting with the silicone, had great biocompatibility and was a flexible material, which is a bonus when you're working inside the body as many parts move, and flexibility is something that is useful. Um, the drawback on the silicone was that it could cause some inflammation. Um, Polyurethane was the next material I analyzed. It had good flexibility and good mechanical properties, was not quite as biocompatible with other materials, so may have more reactions. Some people may not take to it as well. And it was prone to degradation, so over time it would wear down uh, and maybe need to be replaced over time. So that was a couple of the drawbacks of the polyurethane. And then PET. PET is a biocompatible material, very good biocompatibility for blood vessels. Was durable, resistant to degradation, which we saw was a problem in the polyurethane. Um, Unfortunately, it could cause some inflammation, although that did seem to be a common theme among many of the materials I looked at beyond even these ones. So it seemed like a decent trade-off to have the good biocompatibility and durability, um, even if it can cause some inflammation. So here we see testing on one of our vessels. Uh, we ran simulations on 9 models, 3 different materials with 3 different lengths each, 1 millimeter, 10 millimeters, and 100 millimeters in length. Uh, they were 3 millimeters in diameter. Um, those were 3 millimeters was a research number of the size of an artery. I chose to go with the smallest size so that way um, the most stress would be put on the simulations and it could be scaled up from there. Um, from these simulations, we were able to analyze the stress in each of the materials and analyze if those stresses would break the vessel. In this case, actually, all of the vessels tested were viable as a mechanical design. None of them failed. And so we were able to analyze the other parts of each of the materials um, versus the mechanical properties as they all passed the necessary mechanical properties up to 5 times the flow rate that you would see in the human body. The cost of our materials is a major factor in creating these uh, artificial blood vessels because if it's too costly to make, companies won't purchase it for use in hospitals or wherever they may be used. So uh, we started with silicone. Silicone, while it has great biocompatibility, was very expensive at $25 a pound roughly. Uh, The polyurethane had a slightly lower cost than the silicone, but was far less biocompatible than the other two materials, still making it a less than stellar choice for the use in an artificial blood vessel. The PET had very nearly the same biocompatibility as the silicone at a mere 45 cents per pound, which made it the obvious choice for developing a product at a low cost and high biocompatibility. It made the most sense for creating an artificial blood vessel. So as stated, the solution to the problem of creating an artificial blood vessel out of the three materials we analyzed here would be to make the artificial blood vessel out of PET, as it is the most biocompatible and the least cost. And here's some sources that I used to create this presentation. Thank you so much.